So now in this session, we're going to talk about digital circuits and digital information. And this is one thing that I think is a crucial idea for any sort of computer engineer or anyone who's doing computing architecture. So the first idea is well, what are we trying to do when we program a computer? We're trying to take some idea that we have in our head, and we need to translate it into a way that these computing devices can understand, right? Or maybe we're having a conversation, and I need to take the language that I'm speaking in and put it into a language that the computer can speak and understand, right? Okay, so computers, while they're able to do a number of wonderful things, are not intelligent like we are. Computers are very basic in that they only speak one language, and that language is bits. All right? Bits. So what are bits? Bits are just strings of zeros and ones. And so if we want to communicate with a computer, if we want to teach it, tell it to do something, to program it, we need to take our ideas, our language, and we need to convert them into bits. And we have to convert instructions into bits, feed that into the computer reads the bits, and then it does what hopefully we want it to do. Okay, so again, bits are just strings of zeros and ones. So the point of this next hour or so will be to familiarize ourselves with some of the ways that bits can be used for programming. And this is the subject of digital circuits and digital information. So digital information means we take information, we encode it into digits of zeros and ones. All right? And this is going to be kind of a hands-on hour here because there's this really nice tool, this SimCert digital circuit simulator here that we can play around with to get a sense of some of these concepts and how actually you can program or how you can give instructions using digital language. So what I want to do is in a separate, or open up your browser, and let's see, this address here. If everyone can go to it. Okay, I'm going to wait till everyone is there because I'm going to switch. I have it already loaded up in the browser, but the address will go away. So maybe I can write it on the board too. It is in the books, yes. Yeah, right, great. If you got the books open, that's fantastic, yes. Okay. So here it should look something like this. This is what you should see. Okay, now this is a simulator, which means that we can use all of these guys on the left here, and these are simulating real objects that a computer designer has to work with. So you have DC here, which is your power supply. You have an LED, which is going to be the lights that we'll play with. You have some switches here, push on, push off. And you have a toggle switch. And then below that, you have something which are known as a whole bunch of gates. See this? Not, and, NAND, or, NOR. So all those guys on the bottom are what are known as gates. All right? And this is now just the basic building blocks of any computer design are gates. Because this is how the computer processes digital information. So what we're going to do is we're going to try to understand how some of these gates behave. And this is using, what we'll do is we'll put together a few truth tables to monitor this. Yeah?
Just curious, would you call this computer science or computer engineering?
Well, in our undergraduate curriculum, whether you're in computer science or computer engineering, you would take something where you're doing this. So this sort of material, so I taught ECE 100, 110 no, sorry, 120. And we covered this in that. So that, yes. But that was a prereq for both EC and CE majors. Yeah. But if you're doing computer science, you have to understand this. This is sort of the basic stuff. Yeah. All right. So first, let's just play around with this. So if you want to grab your DC power supply and you just drag it over there like this. Okay? And then grab a LED light and bring that onto the sandbox, into the sandbox as well. And the way you want to do is when you click on those little circles, you click and hold it down, and that's like dragging a wire. Okay. So, and if you click again on it, it'll make it disappear. So you click and drag to wire it, and then you click on it again, and it disappears. So let's put a toggle switch on there, and let's go from the DC to the toggle, from the toggle to the light. Okay. And so what this toggle does is it's basically like a light switch, right? When this is down, you get the light to light up. All right, now I want to make this connection with bits, okay? Because right now this is just like some sandbox. But remember, bits are strings of zeros and ones. So we can interpret the state of this toggle as also being in a 0 and a 1, right? When it's pressed, that could be a 1 state. When it's not pressed, it's a 0 state. So what we're observing is a relationship between the state of the toggles and the lights. Right now, this is very simple. When the toggle is pressed, 1, the light bulb is on, 1. When the toggle is not pressed, 0, the light bulb is not on, 0. Okay? But we're going to build up more elaborate circuits, and our goal will be to understand the configuration of the toggles, the states of toggles as being zeros and ones, what that causes the state of the lights to be. Okay, so this is going to be just a very general framework for a logical operation of mapping zeros and ones of toggles to zeros and ones of lights. Right now, this would be the identity mapping. When this is 0, this is 0. When that's 1, that's 1. Okay, everyone got this far, right? Yeah. Very simple. Okay, so let's play around with some of these logic gates to get a sense of what I'm talking about here. Let's first do like the NOT gate. Okay, this one's very simple. So NOT would be like this. And so now we connect it like that. Okay. And we can write this, if we wanted to make a table. Oops. So you could have the toggle. And you could have the LED here. Right? And so the relationship here is when the toggle is not pressed, so that would be a 0, the LED is on, right? And now when we were to press the toggle, the LED would be turned off, so we'd have a 1, 0. Okay? So there we go. This is our first truth table that we built. It's a truth table because it's given a relationship between inputs on the left and outputs on the right. All right? Now, to simplify things a little bit, instead of writing down toggle and LED, we could just call this toggle, let's say, we'll use either X. That's what they use in the book. Yeah, they use X, right. Right, so let's call this X and not X, which is sometimes abbreviated like that. Just put a line on top. Okay, good. So that's the truth table for the NOT gate. Let's do another one. You want to throw in there the AND gate or the OR gate, whichever one. And so now, let me bring it up on my computer. Okay, so the AND gate, you see that there are Oh, by the way, if you want to get rid of one, like say we want to get rid of this NOT gate, just drag and bring it over there to the left side. Okay, so if we look at the AND gate, there's two inputs, two yellow dots, and one output, one white dot. Okay, so that means that this is going to be a function that's mapping two variable input to a one variable output, right? So we're going to need to bring in another toggle because that's going to be another input variable. So let's bring in a second toggle. And now let's just wire it up. So there's still only one LED because there's only one output. Like this. Right. Like that.
Professor,
Yes.
I have a question.
Sure.
Why do you need two toggles?
Well, okay. So you could do it this way, but
Yeah.
what this is saying is that's sending the same inputs. So basically, you're ANDing one input in there,
Okay.
right? So we're actually wanting to give ourselves. We want to introduce a new variable where this will be toggle X and this will be toggle Y,
Okay.
right? It's fine what you did, but that's actually not giving us the full full range of possibilities. Okay. So with two toggles, now we have two input variables. We call those X and Y. Oops, actually, sorry, like this. X, Y. And then what we're doing is we're building X and Y here. Okay. So we have 0, 1. Sorry. So all the possibilities is they can both be off, 0, 0. We could keep the first one off and the second one on. That would be 0, 1. 1, 0, that would be the first X toggle pressed, the second one not. And then this one would be them both pressed. Okay. So what have you guys found in doing this?
Well, you can only use one toggle to turn on the LED.
They have to both be on.
So I heard two things. Both be on. Okay. So that would correspond to this one, right? The 1, 1 when they're both on. So then we get the LED on. Right? And so in all the other cases, they're off. So we would put zeros here. Right? Good. Okay, so this is the truth table for the AND gate. And again, just like conceptually, what this is a function. It's mapping two variables, X and Y, to one variable in output.
I have a question for you.
Yeah.
Okay, so because I was busy looking at this and not concentrating on
Uh-huh.
the actual hands.
Sure.
What were we supposed to do in order to, because I had done the numbers, just logically trying to figure it out without having the program in front of me.
Okay.
What were we supposed to be doing with, to me it looks like a diagram, start program.
Yeah.
So what were we supposed to be doing with the program?
What we're supposed to be doing. So
Diagram, yeah.
Click the toggles and see if the LED lights up.
yeah. So you're pressing these. Yeah. Let me.
So I click the toggle.
Yeah. So right now, you see when you click it once, now it's pressed. I don't know if you can make it out on the screen, but it's actually gray inside.
Yeah, because I
Okay.
pressed it and nothing,
Right.
it was still,
Right.
I'm assuming off.
Right. So the way to interpret this now, this is gray inside, and that's not gray.
Right,
So this, if we call this toggle X and we call that toggle Y,
okay.
that would be like this toggle X is 1 and toggle Y is 0.
And the output is the LED.
And the output is the
And that was
LED.
off.
Yes. So that would correspond to, right now we're looking at this row right here. X is pressed, Y is not pressed, and the LED is off.
Okay.
So maybe it would help if we kind of wrote a table here. So pressed.
Now I'm gonna draw a little picture real quick.
Okay.
So
All right. I'll let.
visually know.
And if you only toggle the bottom one and not the top one, it'll also stay off, right?
Right,
Right, and that would correspond to this
It's an and.
this row here.
right.
It's gotta be the X and the Y before,
Well, both conditions, are we thinking about both conditions have to be met in order for it to come on?
that's the.
Yep.
Sounds like it, yeah.
Yep.
Okay.
That's what this AND gate is doing.
Okay.
But yeah, I mean, and in fact, thank you for your question, because I should have stressed this. The main idea here is that we're representing different states of our toggles using bits, zeros and ones. Okay? And different states of our LED using zeros and ones. That's the whole idea of digital information. Okay, so next question I'm going to ask you guys is, let's switch the gate up. Let's build the truth table for OR.
Oh, I had done that one.
Is there a way to get something off the screen besides, we just drag it out?
You said
The only way I know is just dragging it out. I don't think there's a fast way to delete. So I would grab this AND gate, drag it over here, and it vanishes, and then replace with
Where'd you drag it?
over to the playpen or whatever. Yeah.
Drag it to the left all the way.
Let's see. You getting that? Great. Good. Okay.
Hold on, so this is off. Both of them are off.
Got it?
Yep, I had done it last night, but it came without the picture itself.
Okay. What do we have here?
So that was a 0 at the top, 0, 0, off.
Yep.
Off, on, but that's a 1. I got a,
Is everyone agreeing?
well,
What should go here? A 1 or a 0?
One.
I got a 1.
Okay.
A 1
Yeah.
and a 1.
Yeah. Okay. So notice this this final row here. This is where we sort of deviate from everyday parlance, right? When we say, like, do you want an apple or a banana? Right? We usually assume that you only give one answer, right? It's not like you get both of them. Whereas here, you're getting a 1 when you have both as well. Right? So this would be like an apple or a banana, and you're choosing one. But here, you're also turning this one on when they're both input as well. So what we're used to, I think in the English language, is something not as OR, but it's known as the exclusive OR. And I think if you scroll down and you throw this gate, this XOR in here,
And it has 2 also.
right, yep. So now let's see what this one is. I think in the book it's, call it EOR. Like the donkey.
I see the other one more not asking, do you want an apple or a banana,
Yeah.
but rather, do you have an apple or a banana?
Yeah, right.
The question is,
Do you have, right. So this would be a yes/no answer.
And I'm standing, I've got an apple and a banana both.
Yeah,
I said, yeah, I have an apple or a banana.
yeah. Correct. That's a better way of putting it.
I also have an apple and a banana, but
Right.
it is, if you give me a yes or no answer,
You only
I
need
would say,
one
yes, I have an
satisfier.
apple or a banana.
Right. Or maybe something more dramatic. If you're choosing between two extremes or something. Yeah. So that's right. If you ask, do you have something is a better way.
That's a non-exclusive.
Right. Okay, so how does this one look? Right, okay. Great. Okay. So there are a few other ones there that you could play around with.
Can I ask
Yeah,
you a
go ahead.
question
Yeah.
on the because I wrote a question mark up
Yeah.
here to go just a little bit into depth. Like, so here's the condition with the or and the e-or. And
Yeah.
the or, nothing. I mean, no, on, for the bottom one.
This
Yes.
one, yeah.
Both conditions in this one, and e-or, nothing.
Right.
So, trying to explain the logic behind that one. Like, I don't know, I wrote in here, was this the difference? And
Yeah,
I
so-
thinking like 0, 0, 0, 1 minus.
No, no,
0,
no, no, no,
1,
just,
1 minus 0, 1,
um,
1 minus 1, 0.
okay.
I don't know, just
Yeah.
logically thinking.
So, I don't know if this is going to be very satisfying, but basically what you can take this as a definition.
Right,
All right. So this is defining the OR gate. This is defining the behavior.
right.
And so the OR gate has this particular behavior. This is defining another gate, which we'll call EOR or XOR. Okay. So it's just defining it differently. So it has a different set of rules. And that's really all it is.
Just the behavior.
Right. So yes, exactly. Well, these are just the rules for how it behaves. So you just take it at that.
Okay, sounds all right.
Right. Okay, now with these basic logic gates, you can build up any circuit actually. Any logical circuit, you can use these as building blocks, and you put these pieces together, you can build up a very elaborate circuit. In fact, let's see. So we're going to do some of that. If you want to turn to 13.3, so I'll bring it up here. So I want you guys to try and do this. Okay, so now the way that this activity works is that we're going to have 13 LEDs on our screen, okay? And you want to form an 8 image like this. So the idea here is this is going to be like an LED counter display or something.
You want us to do that?
Yep. So put that into the sandbox. You want to load up 13 LEDs.
Get rid of the power, toggle, all that and stuff.
So you only need one power supply. You just have 13 LEDs.
Okay, so it's a connection.
And then, then the question is, you want these lights to flash in a certain way. And so what this activity is doing is, you want to wire these lights such that it follows, it satisfies the following relationships. So L2 and L8, which would be that light bulb and that light bulb, that is going to be the knot of X. Right, so you're going to have two toggles, X and Y. And now they're going to control the behavior of all 13 lights. And here's the rules of how they behave. So I'll walk you through the first one. Let me bring up 13 lights on mine.
Not a simpler first example.
Well,
It seems pretty challenging. 13 this seems like a big problem to start with.
yeah. I guess doing the full truth table of the other gates. Yeah, fair enough. But it is somewhat satisfying because you see this is. I mean, if you look at old scoreboards, they're designed exactly like this. Because now, basically, using the lights, you can put up any number 0 through 9. So it has a very kind of practical feel to it. All right. So,
Is that XOR supposed to be there?
No, I'll get the XOR out of the way.
Okay.
all right. So the first line here is that the prescription is that L2 and L8 should both be the knot of X. Okay? And the way that I'm going to think of this is that this is toggle X and that's toggle Y. Okay? So I'm going to use the labeling here. So according to the labeling, this is L2 and this is L8, right? So we want to hook these up to the knot of X. So the way we do this is we pull out our NOT gate, and now we just wire it, like here's, like that.
Okay.
Oh, I see, okay.
I'm kidding, the counting 2 and 8. It's a 2 and 2.
Yeah, use your. This is like the labels there. See?
Oh, 'cause I was
Yeah.
like, what?
Yeah, I know. How did I know, right?
I was trying to figure
Yeah, don't count them. Just use the chart in figure 13.2.
out. Okay,
Yeah.
so the knot is 2.
So the knot can make any color.
Yeah, just depends. It all depends on how it's wired. Yeah, sure. Right, you can wire it.
I'm just playing around.
Yeah,
with
yeah,
this.
no.
I don't really- This is all new to me, so.
Right. But that's right. I mean, it all depends on how you wire it. Okay, so now that we have that one done, now the next line is a bit of a bigger set of wires.
1, 3, 5, 7, 10, 12, all equal to knot of X or Y.
So let's talk about how to interpret this.
Our numbering system is left to right, top to bottom.
Uh, Sort of. Yeah, it goes clockwise and then 13's in the middle. So starting at the upper left, you're going clockwise. Yeah. 13. Yeah. Exactly. Okay, so the second set of wiring, it says that you're taking all of those L1, L3, L5, L7, and you're doing not X or Y. Okay, so let's think about what this means. Okay, not X or Y. Okay, so I'm going to draw out what it would look like. So if here's your X toggle and here's your Y toggle, the way to read this is that we first do a not X, then we take that and we OR that with Y. Okay, so the first thing we need to do is we need to take our X and we put it through a NOT gate, which looks like that. And now we want to OR that with Y. And then that's how it looks. Oops, I should probably curl this a little better. Okay, so is it clear? Everyone kind of understand how this not X or Y looks like this in the circuit form? You have your X, Y. You send the X into not, and so then what's going into your OR is the not X or Y, and that's what's coming out. Okay, so then the activity then is you want to hook this output up to L1, L3, L5, L7, L9, all of those, right? Because this output is going to be connected to all of those bulbs. So yes, yeah, that's right.
Not X. Okay, I had not X or Y.
You guys getting it?
So my not isn't on. My, yeah, my not goes there.
Yeah, looks good. Okay, and then the third part is, yeah, holding. Sorry.
So on the toggle for the next one, we're just connecting to the 4 and the 6 from the second toggle here.
Yep, exactly. Yeah. So now we can do the next one. We can connect 4 and 6. And then the last one is the E-NOR, or the exclusive NOR. So that one is, that's XNOR on the, in terms of the gate.
Okay, so it has to be connected to,
X and Y like that.
okay, so X and Y opposed, okay, X, got it.
Yeah.
So we put the more X.
All right. Okay, so let's write down what we get.
Yeah, oh, my stuff came on before I finished.
That's all right. That's all right.
Now it made me negate and turn something off. Okay, so that was supposed to go just to 13?
Just to 13.
Is that the only one that didn't have something connected? I was looking at who. Yep, that was the one that was left by itself. Let's see if it turns some things off now. Ooh.
Okay, so what do you read? What letters come out?
Oh my gosh. Okay, we supposed to click?
Yeah, so now let's interpret. So yep, so they're both off. What letter do you see? I heard an E. I think that's right. Now 0, 1. O. And then 1, 0. Okay. And then 1, 1. Okay, good. Does this make sense?
Yep.
Any questions?
I got lost. I have the diagram.
Great. So now
So
okay, so
what
now
am
this
I
is, see,
doing?
this is 0, 0, because they're not. They're both
They're
off,
both
right?
off, yeah.
Now look at what letter you see.
I'm supposed to see
E.
some letters?
E, right? Look at the lights. See? It's a red.
Okay. I'm like, I don't see anything. I think maybe I need to make sure they're lined up too.
Sure.
Otherwise that they're not gonna.
Thinking like that's the lights on the scoreboard.
Yeah.
Yeah, I can see the invisible little 8 that's usually always up there on the scoreboard.
Yeah.
Got it. Okay, then I need to turn only this one on.
Yeah.
Get the letter O.
And that's letter O.
Okay. Now I'm supposed to turn the first one on and then the second one off.
That's right.
Turn that one on. Are
Nothing.
they all off?
Yep.
Okay. And then turn both on. Okay.
E O H.
Got it.
Wonderful. Okay. All right. So let's leave the LEDs on. We're gonna use them again. But now I want to talk about this idea of mapping bits to decimal numbers. Okay. So when we count, we have 10 fingers. So for us, it's very natural to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we loop around 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You start over again, 21, 22. Actually, it's funny because I have a 4-year-old daughter, and just last night, she got so excited because she counted to 121. And she got stuck at 121. Going to 122 for whatever reason was hard. But that's great progress compared to where she was, where she could only go up to like 19, because something clicked and she understood the way that our number system is structured, and that you have this repetition. So this is called the base of our number system is 10, which means we go from 0 to 9, and then we repeat. So there's 10 numbers. Okay, with bits, it's not 10, it's base 2, because you just have 0 and 1. Okay, so if we need to talk to computers and we need to tell them numbers, we have to convert from our decimal way of describing numbers into the bit or binary way of describing numbers. Okay? And so the way that this works, let's get rid of this for a moment. So this is known as binary notation. And so this is decimal notation. Actually, I'm going to write it on the other side. So decimal notation. Okay. So we have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, these are the building blocks of our decimal notation. And now we want to convert these into some binary number. And binary, we only have access to zeros and ones. Okay, so this is the conversion. Sorry, I'm making this table bigger than it needs to be. Like this. So for 0, we just put a 0 like this. All right. For 1, it's 1. For 2, now we don't have a number 2 here, right? In bits, we just have 0 and 1s. So the way that we write this is 1, 0. Okay? And if you want to, I don't want to get into too much depth here just because of the way we're limited in time, but the way to think about this, like when you write out a number, say 365, okay? You remember how this works? That this is called the ones place. Ones place. This is called the tens place. And this is called the hundredths place. Right. So what are we doing here? Each time we go to another place, we're multiplying by a factor of 10. Okay? And binary, we have the exact same way of doing this, except each time we move to a different place, we multiply by a factor of not 10, but 2. So here, this would be the ones place. This would be the two place, two's place. This would be the fourth place, if we kept going, the 8th place, the 16th place, 32nd, 64th, etc. So because this is the two's place, so 2, 0, so that's 2, right? So we do 2, there's nothing left in the 1 place, so 2 plus 0 is 2. This is why this is 2. Okay. For 3, we want to have a 2th place, 1 in the 2, and then we want to add a 1 in the 1 place. So this is 1, 1. For 4, now we just want to have 1 in the 4th place. So we would go 1, 0, 0. For 5, we have 1 in the 4 place, 0 in the 2, and 1 in the 1 place. So it's 4 plus 1 is 5. 6, I think of 6 as 4 plus 2. So it's 1, 1, 0. 7 is 4 plus 2 plus 1. So this is 1, 1, 1. 8, I just have 1 in the 8th place because 8 is a power of 2. So it's 1, 0, 0, 0. And then 9 would be, I have my 8, and then I have 1 more in the 1th place. Like that. Okay. So now what we'll do is, so this is only has, to keep everything like the same length, we can just add some zeros on at the end here. Like this. Like this. Okay, and so now we've written out the binary representation of the decimal numbers 0 through 9. Okay, and so we see we need 4 bits. So 1, 2, 3, 4. In total, we need 4 bits to represent the numbers 0 through 9. Any questions on this? This is kind of, I went fast here, but this is just the basic kind of ideas of going between binary and decimal. Okay, so now the last activity we're going to do, and this is the challenge for you guys, we're going to use our circuit here. 86, was that it? White lead, okay, good. Yeah. Okay, so let's leave the lights on and clear out the logic gates. So bring these guys back here. Okay, get rid of all the wires. All right, and now your challenge is to do the following. Okay? Wire the lights in such a way that, so let's just focus on rows 1 and 2. Okay, so I'm going to erase everything else. All right, so I just want to focus on rows 1 and 2. And now these are just 2 bits here. So I want to, again, interpret this as our inputs x and y. So x, y, like this. And so this would be 0, 1, 1, 0. And so I want you guys to try to come up with some circuit here such that this truth table is satisfied. So when x is off and y is on, it displays the number 1 here. And when x is 1 and y is 0, it displays the number 2. And I guess there's some ambiguity on how 1 can be displayed, right? You could put it all here or that column. Have your pick.
It's usually the right column.
Is it?
Yeah.
Okay, good. Okay, so the 1 will be on the right column.
Usually there's, I think it goes like a 1.
Yeah, well, for 7-digit display, it's on the right side.
Yeah, but that, yeah. Okay. So I'll give you a hint. First of all, there's not one way to do this. There are many different solutions to this. Here's one hint toward one solution. Remember how and behaves.
Yeah, I wrote it down. So I'm
Right.
gonna look at and.
So x and y. This has the property that it's always off.
It's always off except for both conditions.
Yep, exactly.
So I wasn't gonna look at that.
You got the 1 right? Okay.
You said the one has to be on the right, correct?
Yes.
Okay.
Okay. Yeah. Let's see. Oh, wow.
When both, oh, this is not it.
Okay,
When
okay.
both are off is 1, and then when 1 is on, it's 0. And when just this one is on 3, and like when both of them are, I'm trying to do that. So I managed to,
You're trying. Wait. What do you want to
I
happen?
want both on to be 2.
To be 2.
So I
Okay.
managed to do like when one of them is on, but because of this one, I figured you need it for 1, 0, and 3,
Okay.
but not for 2.
So when they're both on,
Yeah. So
then you want this middle one to go, right?
yeah. So
So what you could do is you could, and that looks a lot like this, right? This is saying that when they're both on, you have that. So if you hook them both up to an and then you plug that to the middle one, you'll get what you want.
what I was struggling with was
Yeah.
actually these 2. Because these 2, I needed for 0.
Okay.
So I needed just for like this one. So not so I want it to be on when this is on, but not when both of them are on. You see what I mean?
Gotcha. I gotcha.
Yeah. So how do I do that? It was not Y or so. Do I have to do like not Y?
Yep. And then and it, right? So
And
yep.
okay,
There you go. Okay, let me give you the solution for the first one. And actually, this is a general rule of thumb or a general prescription. If you want to build up any truth table, you can do it using this method. So you see, what we want is when x is 0 and y is 1, we want this to be on. We want it to display 1, right? Another way of saying this is that instead of x being 0, we have not x is equal to 1. Right? When x is 0, that means that not x is 1. Right? So then what the way to interpret this row is saying is that when not x is 1 and y is 1, we want it to display the number 1. And that looks a lot like this and here, right? Because now you have two things being 1, and you're displaying 1 here. So what you can do then is you bring up the NOT gate here, Okay, so now this is what's coming out of there is not X. And so then if I bring in an AND, I'm ANDing together Y and not X. And now I want this to hook up to all of the lights on the right,
Okay.
right? Because that's the number 1. Just like that. Yeah.
Okay, so I actually did it wrong earlier because we put N for this and it was only turning on for both of them on, but I actually needed when either only this one is on
Yeah.
or both of them on. Then how do I do that?
Oh, then you could do an OR gate or an XOR. Wait, what did you want?
So I wanted like this to be on only when this one
Oh,
is
just
on
hook it right up?
or both of them on. So I needed for two
Oh.
two of the
Well,
four.
when you could directly hook from here to here, right? Then that would could be controlled by this, right?
Oh, okay, yeah. Or, okay, so.
Yeah. Okay, so this gives us 1, and now to do 2, you could do the same thing. The way to think of this is that. So in this case, not Y. Maybe it's a little misleading how I wrote this. Well, for this row, when Y is 0, that means that not Y is 1. Let's see. Okay, I think it's right like this. So not Y is 0 here, and not Y is 1, like this. So now what we can take in order to get these guys to light up, the number 2, we could take not Y and AND it with X, right? And then hook that up to each of the bulbs for the number 2. So if we bring out another NOT gate, and we do, now we want not Y, like that. And we want to AND it with X, like this. Okay, good. So we have the not Y here, ANDed with X, and now we hook it up to all the bulbs that give us 2.
If you hook it up to the same ones that give you 1, the ones that give you 1 disappear.
Oh, they do? Oh. Okay. But I don't think that matters. Let's see.
See how the other
Oh,
goes away when you do?
okay. Yes.
Yeah, you get a 2, like it'll
All right, so then what we need to do is, all right, so now what we do, so whenever there's a repeat, we have to hook it up to an OR. All right, because then it's going to take either one. All right, so if it has a double, sorry, I didn't know it did that. So I guess it's those guys.
and then you put an OR.
Yeah, and then you'd put an OR. So let me finish doing this.
Exclusive OR or regular OR?
In this case, it won't matter.
Any numbers shared by both.
Right, if either one is on, we want those. Or if they're both on, we want.
The ones that are
Yeah, any one. So I guess there's 3 of those, right? Is that? Yeah, these 3. So there should be 3 bulbs that are connected to an OR gate.
top, middle, and bottom of the right side.
Yes. go. And one of the things that people do in circuit design is try to simplify this as much as possible. Right? So clearly you need a wire that's going to every light bulb, right? That is for sure. If those light bulbs are going to be used, we need a wire that goes to it. But all the logic that goes prior to that, there are ways of simplifying it. Now I don't know if actually this circuit can be, there might be a simpler way of doing it. But believe it or not, this isn't too complex. I know it looks complicated. Right. Yeah, this one should. So this is 1 and then 2. Oh, I missed one. Sorry. Oh, the bottom one is shared too. Ah. That one's shared as well. Yeah, so there's 4 bulbs that are shared. These 3 and then that bottom one. Okay. All right, so I think that's pretty much all that I wanted to talk about. Now, this is great because the simulator, you can pull it up anytime you want. And in the book, there's more elaborate exercises. I don't know if you're going to end up building the half adder. I'm not sure what the plans are for, do you know, are they going to? Oh, great, okay. So you will have more advanced implementations of these ideas. Good. Yeah, this was a lot of fun. Yeah. Right. So on the board, remember we wrote down the numbers to 9, and we ended up needed 4 bits. So you need 4 toggles. Yeah. Right, you can go up to 16, but you have to have, because if you had 3, you can only go up to 8, right? So, or sorry, you can only go up to 7 because you need the 4th one gives you 8, and then so the 9 would be it's 9 is 1 0 0 1, right? Yeah, we start counting from 0 when you're doing binary. The first number is 0. It's a little different.